Hello, my name is Ankita Shroff, and this is Lab 4, Circuits and Capacitors in Physics 2212. Today we will be studying the way circuit elements such as capacitors, resistors, batteries, light bulbs, and more interact with each other in a typical RC circuit. I will begin with a short introduction covering the purpose of the lab, the fundamental principles applied, and the results found, and then go into the data collection and questions portion, before ending with a conclusion. So, beginning with the introduction. This lab had multiple purposes. As you can see, our goals were to gain an understanding of the difference in current flow pattern of circuits with resistors in series versus with resistors in parallel. Also, we wanted to learn how to measure the value of current and the potential difference in circuits, as well as understand the interactions between different elements of an RC circuit. In order to accomplish these goals, we needed to apply fundamental principles described here. The loop rule and energy conservation rule are synonymous. They indicate that across the circuit, the sum of the potential differences should be equal to 0, as no energy should be created or lost. The same applies to current conservation. Our last fundamental principle is Ohm's law, which states that for ohmic resistors, voltage is equal to current multiplied by resistance. Moving on to the results of the lab. We saw that the circuit follows the aforementioned fundamental principles. For example, one question in the lab asked us to find the sum of the potential differences across the circuit, and it was equal to 0, as we hypothesized using the loop rule and energy conservation rule. Now to go into the data itself. There were multiple questions in this lab, so I will do my best to summarize as we go. The first thing to consider is the amount of current in the circuit. Based on Ohm's law, the current should equal voltage over resistance, or 3 volts over 147 ohms, which is equal to approximately 0.02 amps. As per the data, the I2 and I1 are both equal to 0.02 amps, which matches our prediction. Next, we see that when reversing the ammeter, nothing changes, and the voltage is equal to 3 volts, which is the sum of the voltage of the batteries, while the current is equal to 0 amps. Moving on, as I mentioned earlier, we are asked to sum the potential differences across the circuit. Based on the loop rule, I predicted that the total potential difference would equal 0, and my hypothesis was supported by the diagram. As we can see, there are 3 individual potential differences that have a value above that non-zero value, which is -3, 0.96, and 2.04, which, when summed, equals 0 volts, thus matching the prediction. On this slide, we see a graph of the absolute value of the potential differences and understand that because of the resistance of the voltmeter, no current is enough to flow through its wires, which shows why there is no change when the voltmeter is added to the circuit. Now we will study the different resistance measurements in each resistor, in the wire, and in the ammeter. This is another place where Ohm's law, which states that voltage is equal to current times resistance, applies. For the 47 ohm resistor, we see that the current is equal to 0.96 over 0.02 volts, which is equal to approximately 48 volts. And for the 100 ohm resistor, we see that current is equal to 2 divided by 0.02, which is equal to about 100 volts. And for the remaining 2, we see that the current is equal to 0 volts. Now we add a light bulb, battery, and capacitor to the scenario. When we do this, for both scenarios, that is, with battery and without the battery, the light turns on, increases in brightness, and then decreases in brightness until it eventually burns out. The same can be said for the current in both scenarios. Now moving on, we study the time that it takes each capacitor, the 10 and 20 ohms, to charge and discharge. It takes approximately 18 seconds to charge and 14 seconds to discharge the 10 ohm resistor, while it takes approximately 32 seconds to charge and 24 seconds to discharge the 20 ohm resistor. We next look at the time dependence of voltage across a discharging capacitor by looking at the change in voltage over 20 seconds, taking the natural log of this, and plotting the results against time to find a graph with slope -1 over RC, with RC being the time constant of the graph. As you can see, the -1 over RC value was -0.1662, which is quite close to the actual value of -0.1667. Finally, I'll conclude my presentation by answering a couple of questions. 1. If we were doing this lab in real life and using an actual ammeter, then that ammeter would be affected by resistance, which would change the circuits that we hooked it up to. Number 2, if we were doing this lab in real life and used a real battery, then that battery would also have an initial innate resistance that would affect the capacitor. Thanks for watching!